Hi again. Before we continue with the example, I just want to point out your attention to an interesting term that we have as a viscous term. A mu Laplacian of the velocity is a viscous term that finally emerges in our Navier-Stokes equation. If we look at this term, we see something actually interesting can be said about this term. So one way to think about it is using this identity from vector calculus, that the Laplacian of something like velocity can be written as del operator or nabla operator acting on the divergence of the velocity, del dot v, minus the curl of velocity. This identity, which is valid not only for velocity but for anything, you can replace v with f, comes from vector calculus. You can easily do that and prove it with Einstein using Einstein notation. But what is interesting here is for an incompressible fluid, this first term is 0 because divergence of velocity is 0. So the first term disappears, and you are only left with this term, which is nothing other than the curl of the velocity, which is vorticity by definition. So indeed, we can actually simplify the viscous terms that we have. And the viscous terms that we have here, which is this term, if we look at them, we can see that mu del to velocity v can be written as minus viscosity mu multiplied to curl of vorticity. So in other words, Navier-Stokes equation is telling us that the viscous term that we have is viscosity times curl of vorticity. So there are two ways viscous terms can diminish. One way is if the fluid has a small viscosity, which is if mu is small, that's this prefactor, then the flow or the fluid becomes inviscid. So you will have condition we called inviscid fluid. But at the same time, there is another condition. You can have even incredibly large values of viscosity for a fluid, but if this term is 0, which can happen in different scenarios with different conditions, but if this term, which is curl of vorticity, is 0, then we will have what we call inviscid flow. And this can happen for a certain class of problems that we did in Module 1, where vorticity was indeed equal to 0. I didn't equal to 0 everywhere. So the curl of a value that is 0 remains 0. Or another case, when vorticity is non-zero, but is constant, for example, the rigid body rotation, that would give us exactly the same condition. Indeed, rigid body rotation is the only example of a 2D rotational flow that is still inviscid. That's something nice to keep in mind. But we can see right now that there are two cases in which Navier-Stokes equation will have no viscous term in it. And if viscous term disappears, we will be left with acceleration equal to gradient of pressure plus body forces per unit volume, which is the rho g term. And that's what we define as Euler equation. So really, Navier-Stokes equation and one layer below it, Euler equation, are all consequences of Cauchy momentum equation. Depending on what constitutive equation we use, we will get different versions of it. In Module 2, we will be dealing with cases that are viscous, and we cannot anymore neglect this term. In Module 1, most problems we saw or dealt with were the ones that this term, for different reasons, either the viscosity was negligible, or this product, the curl of the vorticity, was 0, and we could ignore or neglect completely this term and deal with the Euler equation. With this, I stop this short video, and in the next coming video, we will continue with an example that we can see the solution for Navier-Stokes equation in that example.